Hello, good morning. We continue with the lecture series on signals and systems. So, in this particular chapter, we'll study Fourier series representation for periodic signals. The periodic signals can be continuous time signals and discrete time signals. Let us see what are the different learning objectives in this particular lecture. We'll see how we can represent the signals as vectors. Then we'll understand what is orthogonality. What are the different basis functions which can be used as orthogonal basis functions? Then we'll try to write down trigonometric Fourier series expansion of periodic signals, and also similarly on similar lines exponential Fourier series representation. We'll also understand why the trigonometric functions and exponential functions can be used as basis functions. In the earlier chapter, we have understood that we can use a Dirac delta function or the unit sample function as a basis unit, and then we can represent each LTI system by its impulse response. And then what we do to calculate the response of the signal, response of impulse response of the LTI system to any signal, what we do is we decompose the signal into scaled and translated unit impulse or scaled and translated unit sample function in case of discrete time signals, and then we represent the response of the LTI system to any signal because we can calculate the overall response by using the superposition principle. Now, in this case, on similar lines, in this chapter, we will study how we can use the trigonometric functions and exponential functions as basic unit, and each periodic signal will try to represent it in terms of combination of the trigonometric functions, sines and cosines, or the exponential functions. Right, and if we know the response to any particular uh, mm, sine function, then we can find out what is the response of the signal to sine omega t, then sine n omega t, cos n omega t, and so on. So let us see how we can represent the signals in terms of sinusoids. We can, as I said, we can also decompose any signal in terms of sinusoids or in terms of complex exponentials. The sinusoids or exponential functions are then used as basic units. Now, why we can do so, or what is the reason for selection of trigonometric functions or the exponential functions? So why we are selecting sinusoids? Because when a sinusoid or complex exponential is given as input to any LTI system, what is the output? The output is the same sinusoid or it is the same exponential function, except that there will be a change in the magnitude and there can be a change in the phase also. The sinusoids of different frequencies are orthogonal to each other. This is one more condition required for the signals to be used as basis functions. Uh, we know that sine and cosine are orthogonal, that we know, but sine omega t and sine 2 omega t is orthogonal. Cos omega t and cos 2 omega t, cos 3 omega t, all these are orthogonal. Sine omega t into cos omega t is also orthogonal. That means it is equal to 0. So let us see how we can use the orthogonal set of basis functions, and we can represent it can be used as a unique representation for any particular signal. Unless the corresponding basis functions are orthogonal, the representation that we get cannot be unique representation. So in order to get unique representation, we need to have the basis functions, those are orthogonal. So here we go. What is the condition of orthogonality? Orthogonality of the two signals says that if xt and yt are two signals, xt multiplied by complex conjugate of yt, and if we integrate this between some t to some t dash, then it should be equal to 0. That means these two functions are orthogonal, and when the corresponding xt signal with its own transform when integrated or yt into y star t, if it is equal to 1, then it is orthonormal, right? So orthogonality of sinusoids. So we want to understand that sinusoids are orthogonal. Means we want to understand if we have sine omega t and if we have sine 2 omega t, if we have sine 3 omega t, all these are orthogonal to each other. Similarly, cosine function of omega, 2 omega, 3 omega, 4 omega and so on should be orthogonal, and sine functions should be orthogonal to any cosine function. So sine 2 omega t must be orthogonal to cos 4 omega t and so on. So let us see whether we can integrate sine and cosine functions and we can show that they are orthogonal. So here we are considering the integration over one complete cycle for cos omega t and cos 2 omega t, and when we decompose this we get it as sine 3 omega t, that is this angle plus this angle, and then we get cos of this angle minus this angle, so it is cos omega t dt. We integrate it over one complete period t, so we get half of cos 3 omega t dt, half of integration 0 to t cos omega t dt. Cos omega 3 omega t integration will be sine 3 omega t divided by 3 omega. Cos omega t integration will be sine omega t divided by omega. When we integrate over one complete cycle, any sine function or cosine function will give you 0. Similarly, if we consider this two functions sine and sine omega t and sine 2 omega t, again if we decompose sine omega t into sine 2 omega t, we will get cos omega t minus cos of 3 omega t. And when we integrate over one complete cycle, either it is sine function or cosine function, it should give you 0. Next we consider sine multiplied by cosine. So when we have sine omega t into cos 2 omega t, using trigonometric identities, we can write it as half of sine omega t plus sine 3 omega t. That is this angle minus this angle and this angle plus this angle. And again when we integrate the cosine function over one complete cycle, it will give you 0. Similarly, consider the exponential function, exponentiation of j m omega t and exponential star e raised to means j n omega t. When I write star, it is the complex conjugate, so it becomes minus e raised to minus. So we have to integrate 0 to t exponentiation of j m minus n omega t. Now what is exponential j m minus n omega t? It is exponential j m minus n omega t upon j m minus n omega for m not equal to 0, and if m is equal to 0, it will be equal to t. So it is equal to t for m equal to n, and it is equal to cos minus sine. So this is e raised to j omega t is cos omega t minus j sine omega t. So similarly we are writing here. And when he integrates any cos or sine function over the complete cycle, we get the value as 0. So all sine functions are orthogonal to each other, all cosine functions are orthogonal to each other, all sine functions are orthogonal to all cosine functions. So sine and cosines, we get a complete set of orthogonal basis functions. So we can use it as the basis function. So basis functions are orthogonal functions which are used to find the similarity of the signal width. So when we expand, actually what we are doing is we are taking the signal and we are trying to find the similarity of this signal with sine omega t, similarity of the signal with sine 2 omega t, similarity of the signal with sine 3 omega t, similarity of the signal with respect to cos omega t, similarity of the signal with sine cos of 2 omega t, and so on. And when we write a linear combination of this with some scaling factor, that scaling factor will give you the Fourier series coefficients. So basis function is an element of the basis for a function space. It is a set of functions that can be linearly combined to form a more general set of functions. So all sines and cosines and exponential functions can be utilized as basis functions because they are orthogonal, that we have proved. Now, for example, for simplifying the matter, let us consider any point represented in space. So this is a point P represented in space. What I have is, I have x-axis, I have y-axis, I am representing this particular point in a plane. Then it will be a two-dimensional figure. So I will have only x-axis and y-axis. This x-axis and y-axis, they are always orthogonal, that we know. And then we represent any point P, then it will have unique representation in terms of the coordinates x and y. Now, if I want to represent a point in space, then I'll be using a three-dimensional figure. So there will be x-axis, there will be y-axis, and there will be z-axis, which will be perpendicular to x and y-axis. So x, y and z will be perpendicular to each other, and I can represent any point P with triplet x, y and z, right? And this will be a unique representation. This we already know. So if we are using the orthogonal basis functions as sines and cosines, we can similarly represent any signal in terms of linear combination of sines and cosines, and the corresponding weights, those are assigned to these sine and cosine functions, will then be called as Fourier series coefficients. Now let us see how we can represent the signal as vectors. As I understand, as we already know, that there is a great analogy between the signals and the vectors. See, we have seen the point representation in space. We are representing it as a triplet x, y and z. X, y and z, all these three directions are orthogonal to each other, and we get a 3D representation, right? And we can represent any vector from point origin to point P, any vector, we can represent it by the triplet x, y and z. Any particular vector in a plane can be represented as coordinates x and y. So again it will be a vector, right? So we can consider the signals and vectors. Now let us see how we can find the response of LTI system with input as complex exponential function. So we write the output yt as equal to integration minus infinity to infinity h of tau x of t minus tau d tau, because it is the convolution of xt and the impulse response, that is convolution of the input signal with impulse response of the system will give you the output of the system. So how I can write this? This is equal to ak e raised to j omega t integration minus infinity to infinity h of tau e raised to minus j omega k tau d tau. This is when we are representing, we can represent this particular integration as h omega. This is a complex valued constant. So I can write yt is equal to ak e raised to j omega k t h of omega. This is a constant. So I can write h of omega, because it is a complex valued constant, I can write it as a into e raised to j phi. That means a magnitude and the phase. So I can write yt as a into ak into e raised to j omega k t plus phi. That means when I am using the corresponding input as e raised to j omega k t, in this case x of t minus tau, I can write it as e raised to j omega k t and into e raised to minus j omega k into tau, because it is t minus tau, right? So I am assuming that the input is exponential function with some constant as ak. Then I can get the corresponding value h omega. This is a constant, and then I can write the output of the system as ak e raised to j omega k t. When I write h omega as a into e raised to j phi, then I can write yt as ak e raised to j omega k t plus this angle phi. This angle phi is coming from this particular constant. Right. So if the input is the exponential function, the output is also the exponential function. Only thing is there is a change in the magnitude and there is also a change in the phase. Understood? So any input signal given as input gives rise to the output which is also exponential. This is the basic requirement, right? Fourier series representation of periodic continuous time signals. So why we are using Fourier series? Let us see. Now Fourier series representation is a representation of the signal as a sum of scaled fundamental and its scaled harmonics. So when I say that the signal is periodic, it will have some fundamental frequency and it will have number of harmonics. But what is the amount of harmonic? The second harmonic may be dominating, third harmonic may be not there, fourth harmonic is having very small value, right? So we represent the signal as a sum of the scaled fundamental plus its scaled harmonics. The harmonic amount of harmonic that is present is the corresponding scale that is used for that particular harmonic. We have to find out the amplitude of the fundamental and the amplitudes of the harmonic frequencies present in the signal for writing down a Fourier series for a signal. These amplitudes will then be called as Fourier series coefficients. So when I write the signal xt as equal to some constant 0.4 into fundamental plus 0.3 into cos omega t, omega 2t plus 0.3 into cos omega 3t, then 0.4, 0.3, 0.5, these are called as, these constants will then be called as Fourier series coefficients. The Fourier series coefficients will represent the degree of matching of the signal with the corresponding harmonic component. So what we do is we are having basis functions. Basis functions means we are having some scales. What are these scales? I am having one scale with the as a fundamental, second scale I am having as the second harmonic, third scale is the third harmonic. Now I use that scale and try to measure the signal. Now how far it matches with the fundamental, how far it matches with the second harmonic, how far it matches with the third harmonic, that I go on finding out and then write down the signal as the combination of linear combination of the scaled fundamental plus scaled different harmonics, scaled versions of different harmonics. That is called as Fourier series representation, and the corresponding scales will then be called as Fourier series coefficients. So let us consider the Fourier series representation of a periodic signal. If the signal is periodic, there will only be the fundamental and number of harmonics, those will be present. So Fourier series expansion of the signal is equivalently resolving a signal into sum of sine and cosine functions. So I can write the expansion as, this is xpt is the periodic signal. We are writing this subscript as p because it is a periodic signal. So xpt is equal to a0, that is constant because the corresponding signal will have some DC component also. Then it will have the fundamental and there will be number of harmonics. As this n varies, n is equal to 1 means it is the fundamental, n is equal to 2, 3, 4 means it will be second harmonic, third harmonic and so on. And these corresponding coefficients with which we represent the second and third harmonics will then be called as Fourier series coefficients. Now how to find out this an, bn and a0? Let us see. There are some conditions, those are required to be fulfilled. These conditions are called Dirichlet conditions. Now what are these Dirichlet conditions? The first condition is the function is a single valued with the within the period. So if you consider one complete cycle of the signal, then it must be single value. Means there should not be two or three values for the same time t in the signal. For a particular time t, there must be only a single value of the function. It must have only finite number of discontinuities. It can have finite number of maxima and minima. Suppose you consider a sine wave, sine 100 means a sine wave with frequency of 100 hertz. Then it will have number of maxima and minima, but those will be always finite number, right? The function is absolutely integrable. It should be absolutely integrable means when I integrate from minus infinity to infinity, it must give me some finite value. Why Fourier series for periodic signals? Fourier series decomposes the signal into linear combination of scaled sines and cosines. Sines and cosines are orthogonal functions and hence the decomposition is unique. I have told you that in order that the decomposition is unique, the corresponding basis functions must be orthogonal. That is why we have proved the orthogonality for sine, sine, cos, cos and sine, cos functions, right? The periodic functions encountered in practice, all these satisfy the Dirichlet conditions. That is why we are using the periodic signals for representation of the Fourier series. Now, let us see how we can evaluate these constants, that is Fourier series coefficients A0, An and Bn. This is, we say, that generalized representation for the periodic signal in terms of the Fourier series. So we write it as some constant DC value plus the first harmonic, second harmonic. So as n varies, we are representing different harmonics, and the corresponding coefficients an and bn are the Fourier series coefficients. So let us see how to evaluate this. In order to get a0, I'll have to just integrate this xpt over one complete cycle, that is between t to t plus capital T, where capital T is the period. So when I integrate, what I'll get a0 integration t to t plus t dt, so it will be a0 t. So what will be a0? A0 is 1 upon t into this integration. So how I evaluate a0? I'll have to evaluate this integral for the signal over one complete cycle. Now, if I want to calculate an, what I will do? I will multiply this xpt by cos n omega t, right? And when I multiply it by cos n omega t, I get on the right hand side, I get a0 cos n omega t, that will integrate to 0. Then an cos of uh, this is cos n omega t into cos n omega t. So when m is equal to n, we have seen that it is equal to 1. So in this case, the corresponding integral will give you the value of t by 2. So in this case, we will have the corresponding output an is equal to 2 by t, and we'll have to integrate this by multiplying it by cos n omega t. And if you want to calculate bn, you will have to multiply this xpt periodic signal by sine n omega t and integrate, and then multiply it by 2 by t to get the value of this corresponding Fourier series coefficient. Is that okay? So these are the formulae that you will have to remember how to calculate the corresponding coefficients, Fourier series coefficients for a sine function and for the cos function. Okay. So if it is Fourier series expansion using exponential terms, then I'll have to write the corresponding exponentiation coefficients as a0. This is also obviously the constant with the DC value. Then correspondingly for n equal to 0, it will be an minus jbn, and for n less than 0, it will be an minus jbn. So these formulae to be utilized for exponential Fourier series. So I will explain you how to solve a particular example. So let us say we are given xt is equal to 5 cos of pi by 3t plus pi by 6. This pi by 6 is a constant and it is just a cos term. Now what is the fundamental period that we want to calculate? So compare this with 2 pi t. 2 pi divided by capital T is your omega. So omega 0 is pi by 3. I can write it as 2 pi by 6. So what is capital T? Capital T is 6. Now I will write this x of t as equal to 5 cos of pi by 3t plus pi by 6. Now I will write it in terms of exponential values, exponentiation terms. So cos of theta is e raised to j theta plus e raised to minus j theta by 2. Now in this case, this is 2. I will just expand these terms. So 5 by 2 e raised to j pi by 6 into, this is a constant that I have taken out, and this particular term is e raised to j pi by 3 into t. Similarly, it will be 5 by 2 e raised to minus j pi by 6 minus j pi by 3 into t. So in this case, this is a constant, this is also a constant, and what is the corresponding period for this? The period is equal to 6. So this will be for k equal to 1, this will be constant for k equal to minus 1. So x of k, I will write it as 5 by 2 e raised to minus j pi by 6 minus j pi by 6. This is for k equal to minus 1. 5 by 2 e raised to j pi by 6. This will be for k equal to 1, and there is no constant term, so corresponding value will be equal to 0 otherwise. So for k equal to 0, it is equal to 0. So if I want to write the Fourier series so for using the exponential terms, how do I write? This is the corresponding constant for k equal to minus 1, this is for k equal to 1, and at the center, that is at the DC value, is 0. So how do I represent it as the magnitude and phase plot? So because it contains only one particular cosine term, there will be one spectral line for k equal to 1, another spectral line for k equal to minus 1, and the corresponding angle is positive for k equal to 1, angle is negative for k equal to minus 1. Now k equal to minus 1 means these are the negative frequencies. Why negative frequencies are there? Because we are writing the corresponding exponential representation. Exponential term e raised to j theta is equal to cos of j theta plus e raised to minus j theta by 2, or we can write cos of theta is equal to e raised to j theta plus e raised to minus j theta by 2. That e raised to minus j theta is giving rise to this term. So only because we are using exponential terms, we are getting these negative frequencies. Otherwise, there is no meaning attached to these negative frequencies. Remember, we are supposed to consider only the spectrum on the positive side. We just replicate it on the negative side because we are representing exponential representation. We are using exponential terms. Otherwise, this particular negative side need not be plotted at all. Consider one more example. Xt is equal to twice sine 2 pi t minus 3 plus sine of 6 pi t. Now compare it with 2 pi f. So in this case, frequency is equal to 1. Here, what is the frequency? It is equal to 3. So what is the corresponding, you can say, capital T? It will be 1 by 3 here. It will be 1 here. Okay. So xt is equal to summation k equal to minus infinity to infinity x of k e raised to j k 2 pi t. This is the generalized representation in terms of exponentiation functions. Now each of this sine function, I will write it as exponential term. So sine of 2 pi t minus 3, I will write it as e raised to j 2 pi t minus 3 minus e raised to minus j 2 pi t minus 3 divided by 2j as per our formula. Now sine of 6 pi t, I will write it as 1 upon 2j into e raised to j 6 pi t minus e raised to minus j 6 pi t. Now when I simplify, this 2 will cancel. 1 upon j is nothing but minus j. So if I simplify 1 upon j, e raised to minus 3j, this is the constant term, and e raised to j 2 pi t minus e raised to 3j, this is the e raised to plus 3j, this is the constant term, and e raised to minus j 2 pi t, this is for the fundamental, plus 1 upon 2j into e raised to, sorry, this has to be e raised to j 6 pi t minus e raised to minus j 6 pi t upon 2j. Now, what will be the term for k equal to 1? K equal to 1, I will have to use this particular constant. So, 1 upon j e raised to minus 3j. So, how shall I write it at? It is equal to minus j e raised to minus 3j. Because 1 upon j, if I multiply the numerator and denominator by j, I will get it as minus j. And for k equal to minus 1, this particular constant will come into picture. So I will have j e raised to 3j for k equal to minus 1. Similarly, for k equal to 3, because here the frequency is 3, 6 pi t. So if I compare it with 2 pi t, 2 pi f into t, what is f? F is equal to 3. So the corresponding coefficient is for k equal to 3. What is the coefficient? 1 upon 2j. So I can write it as minus j by 2, and it is equal to j by 2 for k equal to minus 3, equal to 0 otherwise, because there is no DC term at all. So corresponding magnitude and phase response I can write. The frequency terms are 2. This is fundamental and this is the third harmonic. Then we are replicating it on the negative side also, because we are using exponential terms. Otherwise, negative frequencies have no meaning. Similarly, if I am plotting the phase, for this phase is negative, phase is negative. In this case, the phase is positive. Okay. So this is how the magnitude and the phase plot will be plotted. I hope you have understood. Thank you.